Welcome to our third note set in the second unit of the digital audio signal processing course. The second unit is on filters. And in the last unit, in the last note set, we looked at some classic analog filters. And here, given the title there, you can tell that we're going to be talking about discrete time filters. I base my presentation here on this book by Laffey. It's covered in a lot of signal processing books. It's also covered in a section of the digital audio signal processing book by Zulzer. So there's lots of places you can get readings on this. And I don't think I follow exactly either of these two because I have my own way of thinking about it, but it all comes out in the wash, so to speak. So why are we considering so-called recursive filters or IIR filters in this course? You may have learned about FIR filters and their design with the Parks-McClellan algorithm, and maybe you learned that that's a premier way to design filters. It is, but there is, in audio, there are some reasons that we want to look at IIR filters. So first, just more generally, not audio specific, but just generally, the real advantage of IIR or recursive filters is that you can get a really good filter with a low order filter. Obviously, the higher order you go to, the better the filter is going to be, whether it's FIR or IIR. But if you're looking for, good transition bandwidth and good stop band attenuation and all that, those kinds of things, you can get the same performance with an IIR filter of lower order than you can with FIR. And that then leads to computational efficiency. So that's an important thing. For audio in particular, it means that we can very easily adjust the cutoff frequency or the center frequency or the bandwidth with just a few parameter changes, whereas for an FIR, you pretty much have to change all of the coefficients, and it's not in any obvious way. So that makes it hard to implement some sort of user adjustable filter. So IIR filters have an advantage there. And we can often just rely on designs of second and fourth order, maybe throw a third order in there as well, filters, because we can then just cascade them into making higher order filters. So that sometimes simplifies the design process. But here's another reason for this, especially tailored towards audio. We just spent the last note set talking about lots of classic analog filters. Those are beloved in the audio world. And if we're going to be doing audio with digital signal processing, we might be asked to mimic these classic analog filters. So there's a very simple design process that allows us to start with some desired analog filter and then apply this thing called the bilinear transform. That's the focus of this note set. And it will convert that analog filter into a discrete time filter that is as close to mimicking the original as possible. There are always going to be some issues involved with the sampling of signals and the discretization of the filter. Will lead to, well, let me say it this way. Discrete time filters can only work up to a certain frequency, the FS over 2 point. And beyond that, they don't really do anything. So we have to be careful. And this may be a case where you bump up the sampling rate just by a factor of 2 or 3 or so to apply a filter without that kind of boundary or barrier of FS over 2 getting close to the audio range. That might be overkill, but it certainly is something that can be done. I alluded to the Parks-McClellan design process for FIR filters. That's in MATLAB, the FERPM and the FERPM-ORD. Oops, I missed a P there. That should be FERPM-ORD. So the PM here is Parks-McClellan. We're not really going to cover too much on FIR filter design. Well, we're not really going to cover anything at all. If you want to see that, go back to my video for note set 29 from my 301 course on signals and systems. And I give sufficient detail there for you to learn how to apply those commands. But we're not really going to need this anywhere in this course. Okay, the challenge with this note set is the notation, because we've got two things going on. We've got this desired analog filter who we want to mimic, or that we want to mimic, I guess would be more grammatically correct. And we've got the discrete time filter that's doing the mimicking. And so we need to have some notation to keep these things straight. So it's not quite exactly the same, but I like to liken this to the scenario of making a scale model. So you need to have your scale for the physical reality. So say you're going to make a scale model of a car. So you've got regular feet, and then you've got equivalent feet for your model. That's kind of what we're doing here, although it's not exactly correct because it's not a proportional scaling. It's kind of a warped scaling, as we'll see. But the idea is you need to keep straight two different scales, essentially. Okay, and so notation will help us keep track of all that. So we've got our continuous time analog filter. It's got some sort of transfer function, and I, in this note set, put an A up there. In other note sets, I've put other things up there, like an L or maybe an S to show that this is the Laplace transform. I forget what subscript or superscript I put up there in other ones. But in this note set, and then when we use these ideas elsewhere, I'll generally put an A up there to let us know that that's the analog filter. So that's the transfer function. And then if I want to get the frequency response from that, here's the notation that we're going to use here. We're going to keep the same function and just replace S by J omega. And so that's what we mean when we write something like that. You take the S function, replace S by J omega. Now remember that omega here is in radians per second. So this is the continuous time frequency. Okay, we could convert that into F by dividing that omega by 2 pi. Now here's a picture of what's going on. This is from the operational amplifier book that I learned from back when I was in college. So this would have been a early 1980s publication date probably. But I just borrowed the picture there because I was aware of it. So this is a plot of the magnitude of the H of S on the left half side of the S plane. And then we've cut along this axis. That's this action of replacing S by J omega. We just look at the function looking in from here. That's the cut along that axis. That gives us the frequency response. Now, we've got some digital filter that we're hoping will mimic this. So if we take a signal, sample it, put it into this digital filter, and then unsample it, from end to end, we hope that they look kind of virtually the same. There will be some differences, but you tell me how negligible you want those differences, and I can make that happen. It might just require more processor power and cost and so forth, but it can be done. Tell me how close, and we can do it. So this is a new filter, discrete time, and so I put a D up there to denote digital or discrete. And then we do the same thing we will replace z by e to the j capital omega. Now that capital omega is in radians per sample. And remember, we only care about that frequency from minus pi to pi. Outside of that range, it's 2 pi periodic. And then this is the same idea. We're replacing z by e to the j omega. That means we're evaluating this z transform on the unit circle, right? This is complex numbers whose magnitudes are 1 and can take on any angle around the circle. And so it looks like this. That black curve there is the height of the magnitude. I say x here, but it really should be h. I just borrowed this from one of my other note sets somewhere. That is the magnitude of this h of z, this h superscript d of z, evaluated on the unit circle. So that's the frequency response shown on the circle, but we usually like to lay it out on an axis of omega. And it's this circle that leads to that 2 pi periodicity, right? No matter where we go around the circle, however many times we go, we're back to one of the original places. And so that's where that periodicity comes from in this mathematics. And so if we unwind that or unwrap that, so we cut it here at the plus or minus pi juncture, and we unwrap it onto this omega axis, it might look something like that. So that's our frequency response, magnitude in this case, evaluated around the unit circle, cut and unwrapped. But remember, it's 2 pi periodic in each of these directions. I'm not showing that here, but we need to know that here. Okay, so I'm talking here about many views of the discrete time frequency. So this is a convenient variable to use when we're just talking theory, or maybe even just worrying about, some sort of design issues. But this is in radians per sample, and it has no connection to the physical real world. Remember, we want to see, how does this filter mimic the desired analog filter? So we really need to connect these discrete time frequencies to the physical real world. And so that comes through the sampling rate, right? Pi here, sample radians per sample, corresponds to fs over 2 hertz. So we can draw an equivalent frequency axis in hertz. So if we were to take a signal, sample it at fs, run it through this filter, this frequency response plotted on this axis would tell us the effect of that filter on the various physical frequencies of that original continuous time signal. And here I'm just pointing out that capital T is 1 over fs. And here's the mapping. We could write this in terms of little f over fs if we wanted to write it that way, but it's convenient to write it for this view right now in terms of capital T. But really, that's nothing more than just remembering that pi maps to fs over 2. Now, there is another mapping that will be convenient here, since for the continuous time filter, when we're really talking about filters being applied in real-world scenarios, we generally like to talk in terms of f, in hertz. You never hear an audio engineer, rarely anyway, saying, oh yeah, bump it up a little bit at 900 radians per second. Nope. We're always talking in terms of hertz. Bump it up at, whatever, 1 kilohertz or 500 hertz or whatever. So, but theoretically, it's easier to work things in terms of little omega. So let's convert this to little omega. So if we use our conversion between f and omega, so 2 pi f maps to little omega. So that's hertz into radians per second. So we've got radians per sample, hertz, which is cycles per second, and radians per second. These are our 3 units that we care about. And this makes a nice little relationship. Capital omega can be written as little omega capital T. Just a word of warning, there are some DSP books, like Proacus and Monolacus, reverse the roles of these, so be very, very careful with that. That's one reason I don't particularly care for Proacus and Monolacus. A good book otherwise, but I find that a little jarring. So I always have to remind myself that. But I'm going to stick with this is discrete time frequency, this is continuous time frequency in radians per second. But we've got a mapping between all of these things. And then if we think about it, here's our discrete time frequency response as a function of omega, just like we showed it here. If we plug in this mapping, we can write it in terms of its equivalent omega. Now, we could just as easily have plugged this in there, and that's how we get the function that we could plot on F. But for our purposes for right now, since our H superscript A is going to be easier viewed in terms of omega, we'll do it this way. Then when we get the final design, we're going to want to plot it versus F in hertz so that we can see what it really does. So we're going to use this second form so that we can view it as a function of radians per second frequency. Okay, so now that we've got that out of the way, let's talk about what it is that we're trying to do. So here is our given target continuous time filter. Whatever it is, we've got the transfer function, and we're imagining putting a signal in and getting a signal out. And you've learned in your signals and systems class how to analyze that, right? Convert this into X of S. Think of this as Y of S, and the product of these two things gives us that thing. So you've studied that. Now we're going to say, imagine that we take the output of that system and we sample it. And then equivalently, we take whatever discrete time filter that we're hoping will mimic our desired analog filter, we put an A to D converter in front of that. So now we can compare these two things. Now, let me back up and just say I could not put that there and put a DAC here and then look at, the equivalent Y of T that comes out. That's one way to do it, but this way, and that's really more like what we would really have, right? In the physical real world, we would have this filter and then this one followed by a DAC, and we'd say we want these two things to be equivalent to each other. But for the mathematics that we're going to do, it's a little more convenient to set it up this way, which is essentially equivalent, right? I'm going to take this signal and sample it. I'm going to take this signal and sample, and we want these two things to be the same. That's our goal. Given this, choose this so that those two things are the same. Now, that may seem like a tall order, and it is actually. In fact, it's something that we can't make happen exactly. That's the challenge with this. But a way to approach this is to, let's say, hey, we know Fourier tells us that every signal can be built out of some sort of combination, whether it's an integral combination for a Fourier transform or a sum combination for a Fourier series, but every signal can be built from some combination of sinusoids. Now, let's extend that just a little bit farther and say, well, Fourier told us that. Laplace actually tells us that every signal can be built from some linear combination of more general sinusoids. So let's look at this fundamental input signal, e to the st, because that's the thing that Laplace tells us, if I can figure out how that goes through these two filters, then that will enlighten me to how everything goes through, or anything goes through these two filters. So we're going to put that in here. And so let's take a look to see what happens right here. After the A to D converter, assuming that A to D converter is perfect, there's no quantization and no issues with it, it's just perfect. replace little t by n capital T. Now we get e to the SNT, and then we just say, well, if we define z to be e to the st, we can just write this as z to the n. So notice we're limiting ourselves to very specific z values here. So that's the thing that's going in. So we could think about this signal going in as some specific z to the n. And the z transform tells us that is the thing that goes through that system in a fundamental way. So the nice thing is we've got the two fundamental scenarios happening side by side here. So from our study of Laplace, we can say if I put an e to the st into this filter, the thing that comes out here is just ha of s e to the st. Now, just a subtlety here. Here we're thinking of s as some arbitrary but fixed value, right? So it's like a generalized frequency. And this is some sort of generalized sinusoid at that s frequency. But this holds for all s, so we can think of it as a fixed relationship that can vary as we change s, but it will always hold true with that relationship. And then let's do the same thing down at the bottom. So if we put in z to the n for some fixed z, the thing that comes out is you evaluate the frequency or the transfer function at that fixed z, and that's what comes out. But we're doing it for a very special fixed z that's related to the s that we fixed up there. So we can boil that down to that. So now let's do this last step. So we've got this here, and now we've got this, so we need to get to that. So let's sample that thing, and now we end up with something that looks like that. And there's the goal, right? We want to make these two things equal to each other. So what do we see? They both have that multiplying something. So these two things have to be equal to each other for all possible s values. And so that's the goal. So what that says then is if we want a discrete time filter that will mimic this given continuous time desired filter, we need to choose it such that if we replace z by e to the st, it equals our desired function. So that's the thing. So now the trick becomes, how do we pick such a filter? That's the goal. But it doesn't tell us how to pick it. It just tells us what we want to happen. So I'm just rewriting that here. And that's the goal. And now, in other words, what we're saying is we would like to come up with some magic function g of z so that when we plug it in here for s, it boils down to an h superscript d of z, that when I replace z by e to the st, boom, I'm back to my desired function. That's the goal, or that's our design trajectory that we're trying to have happen. So in other words, if we look at this, we need this thing when we replace z by e to the st in whatever that function is, boom, it just boils down to s. If we can find that g function, that'll be the magic mapping function. Well, unfortunately, the functions that meet that exactly end up having some problems that don't lead to good filter designs. I don't go into those here. We're just going to skip over it, but just trust me, you don't want something that will do that exactly. So now, we have to fall back and say, well, if I achieve that exactly, I don't get what I want because there are some weird things that happen, and it's mainly due to the periodicity of the discrete time frequency response. So now we need to fall back and say, well, let's find something that approximately satisfies this, but doesn't have these other serious issues. And again, I'm kind of going through this without covering a lot of the details like might be covered in a full DSP course. So here's the proposal. There's my function. It's got z minus 1 over z plus 1. We're going to call this the bilinear mapping or the bilinear transformation or the bilinear transform. It's not like a Fourier transform or a Laplace transform. It's more like a mapping. So it really should be called the bilinear mapping, not the bilinear transform. But we call it bilinear because there's this linear thing here and there's this linear thing here. That's why it got its name. Let's see that this thing approximately satisfies this. So here's the thing. I'm going to replace z by e to the st. So there's my two z's that get replaced. And then here's a little thing that pops up a lot in signal processing analysis. We see an e to the something minus 1 or plus 1, and we can factor out an e to the minus st over 2. And we can factor out an e to the minus st, or we can multiply, not factor out, we can multiply top and bottom by that. It's equivalent to factoring out, but if we now multiply that through, we end up getting this kind of thing, a plus argument and a minus, a plus and a minus. That's a classic trick, good thing to remember. And look, this kind of reminds us of Euler, right? But Euler is a e to the j thing. The j here is not explicit in S. S is not a purely imaginary thing. It's a complex thing. So this is a generalization of that. And if this were e to the j things here, we'd get a tangent. But without that, the mathematics tells us it has to be what's called a hyperbolic tangent. So that's just by definition of the hyperbolic tangent. And you probably saw this back in your calculus class, and you probably went, oh, that's weird. I don't think I'll ever need that. Guess what? You do. Here it is. And then, once we have the hyperbolic tangent, we can expand that in power series. Oh, Calc 2 coming to your rescue. So if we expand that out, again, not going into the details, you can look it up. Look up what's the power series of a hyperbolic tangent and then apply it to this form. And you get something that looks like that. And then here's the key. Remember, we're sampling pretty fast. So that capital T is the spacing between the samples in seconds. That's pretty small. So for audio, we're talking, a couple tens of microseconds. So if T is small enough, look, T cubed, T to the fifth, these things will be negligible compared to just a T. And so what ends up happening if we say those are negligible? Those all go away. The T cancels, the 2 cancels, and we're left with approximately equal to S. So it satisfies this approximately. That's why this works. Plus, it does not suffer these serious issues. So it works approximately, and it gives us filter designs that are nice. So let's see this. So here I'm calling attention that this is a mapping to the Z domain via the bilinear transform. It's not like a Z transform or anything like that. So I don't really like the name transform. But here's the idea. If we replace S in this by all of this machinery, we'll get a discrete time filter, and it will approximately behave the way that we have set out to say we want it to behave. So this is all in terms of transfer functions, and that's nice from a design point of view, right? You start off with your transfer function, you map it into a discrete time transfer function. You now know the design of it, but what does it look like? What is the frequency response going to be? Well, we know how to do that. We know how to take the Z here and replace it by that. And now notice I've used a omega sub D here. That's going back to my comment about, think about, we're making a scale model, right? We've got our length on the reality and we've got our length on the model. Okay, so this is going to be lengths on our model. And so we can write that out more explicitly like that. And then using this idea, here's where the z's show up. We replace those z's by that. So now we have a way of linking this as a function of its frequency that it's going to be working on to that same frequency variable inside the function for our desired analog filter. And now I'm just going to do that same little trick, right? I see an exponential -1, exponential +1, and I multiply top and bottom by e to the minus j thing, and I get something that looks like those two things. So like I said, that's a good trick to remember. Aha! But now this really is looking like Euler, right? E to the plus j, e to the minus j, and we've got a minus and we've got a plus. So one's going to be a sine and one's going to be a cosine. And then when you do sine over cosine, you end up with a tangent. And you end up with a little j out in front. If you work through all the details, you'll see where that comes from. And so notice that that is the thing that is inside the analog filter's frequency response. So that looks like the frequency that the analog filter would be operating at. So let's think about it this way. If the analog filter, if you look at something that's happening at this frequency in its frequency response, it'll show up over here at that frequency. So that's the idea. So let's map this back the other way. This is mapping omega d to omega sub a. We want to know, how does our reality map to our quote unquote scale model? So here's our reality, here, or not reality, but here's our thing that we're trying to model, and then here is the frequency in our model. And so we just inverted this tangent. So we get this inverse tangent here. So what this is telling us is that some sort of feature in our analog prototype that is at some frequency omega sub a will show up in the design at this point. That's the idea. And we're going to see on the next slide that this inverse tangent function, it's like building a scale model that's not linearly scaled. Some parts are close to linearly scaled and other parts are just kind of warped in to fit. Because remember, everything needs to fit in the, minus pi to pi in the capital omega. So let's take a look. Here's that inverse tangent. There's that function that we just looked at. Here's our prototype's frequency axis. Here's our target or our design frequency axis. And remember, this is in radians per sample. This is pi over capital T. If we map that back to capital omega, that maps back to pi. So there's our 0 to pi range. And it would be 2 pi periodic outside of that, which is not being shown on this plot. But here's the important part. There's this frequency warping that's happening. High frequencies in our prototype get mapped to much lower frequencies in our digital target, right? These should be mapped. Here's the line omega d equal to omega sub a. Let me just pick something here. This, if we were mapping it directly, would end up way up there, but it ends up way down here. So we're squishing in the high frequencies. Let me show you a picture that will make it a little clearer. On the top, that's our desired prototype. That's the classic analog filter, perhaps, that we want to design. I just drew it by hand with PowerPoint, so it's no special, Butterworth thing or anything like that. But suppose that's the thing that we want, and I'm trying to indicate the cutoff frequency there. And this thing goes out to infinity, as all analog filters do. But now let's look at this mapping. At low frequencies, things map almost perfectly one-to-one. So down here, this point, this frequency maps to this frequency. So that means this point ends up there. And this frequency maps to this frequency. So that ends up there. And so on. But as we look further out, so out here, this frequency here maps all the way in to here. So it gets mapped in. It's got to be inside the pi over t. So this little point here maps to this little point there, and so on and so on. All the way out to the thing at omega sub a equal to infinity maps in right here. So this part's being mapped almost one-to-one, but with a little bit of squishing, right? A little bit of warping. You see that the cutoff frequency ends up being less than desired. We'll come back to that point in just a little bit. And then all this extra stuff up here gets squished in. So it's like, imagine having an infinite rubber band and we leave some of it pretty much mapped straight down, and then the rest of it we kind of let go and let it squish in. That's kind of what we're doing. But it's all characterized by that warping function. So people say that the bilinear transform warps. And then I point out, remember, this frequency response doesn't continue on. Discrete time filters. So that's our 0 to pi range in the capital omega variable. And so it repeats periodically, which I'm not showing here, but we have to remember that that is there. It's not part of this mapping. This mapping just maps the full frequency response into one, the main region on the capital omega axis. And then we have to remember there is the periodicity involved. So what if we want the, say, cutoff frequency to be exactly where we want it? So let's go back and look at this previous slide here. We said that the center, or the cutoff frequency for our design, ends up being a little to the left of our target. So what if that is not what we want? So here's how we could do that. We start with a filter that is actually moved out a little bit. So suppose this is actually not our desired cutoff frequency, but we tweaked it upwards just a little bit before we applied the bilinear transform, so that where it ends up is exactly where we want it. And we know exactly how far it gets mapped down, so we should know if we want it to end up here, we should know where we need to put this. So in one sense, we're going to start with our desired prototype, tweak it upwards a little bit, and then let the bilinear transform tweak it back down. And that's called pre-warping. And we can go into a lot of details on that, but I'm not really going to go into it. If you work through the details, and there are things in the books that will tell you how this works, but we just want to get on with doing some audio signal processing here. It turns out that we can do this pre-warping very easily if we define a number k this way with this tangent function, and we put in the frequency of whatever feature we want to be placed precisely. So cutoff frequency, center frequency, whatever it is, those are the two most common things that we want to end up in the right place. So we put that number in there. We put in our sample spacing that we're going to run the filter at, and we compute this k number. And then we modify the bilinear transform. So remember that we put, what was our bilinear transform before? Let's go back and see what it is. It was a z minus 1 over z plus 1. That part doesn't change, but we had a 2 over t. Let's see how we modify that. Now, instead of having 2 over t, we have this omega 0 over k. And if you look at that omega 0 over k, you can see that If you were to undo the tangent on that, you'd end up with omega 0 over omega 0 over t over 2. And the omega zeros cancel, and you end up with 2 over t, which is what you would need to have. So that's why this works the way that it does. It reduces down to the desired when you just don't put the tangent, or the original, not the desired, the original BT, when you don't put the tangent in there. So that's a nice way to think about it. So now, instead of mapping with that original bilinear transform, we map with this. So we have a functional form for this. Everywhere there's an S in that original prototype transfer function, we now plug that in, and we can do a bunch of algebra, and it'll work out. But more importantly, here's the thing. When we plug in omega 0 into our design, it takes on the value of the desired at exactly that desired cutoff frequency or center frequency or whatever. All right, this may be clearer if we go through a simple example. So here's a simple first order filter with a cutoff frequency of omega c radians per second. And let's design it with pre-warp. So that means we're going to take this thing, everywhere there's an S, we're going to replace it by this thing. And then we'll have a function of z, and that will be the function of the filter. And I put a subscript here, PW, to show that it's pre-warped. So there I am plugging in for S this quantity. And now I just do a little bit of algebra. And I did it so that I get z's by themselves. So I'm getting polynomials in z over polynomial in z. And I've just grouped things into, kind of nice forms here. And remember, K here is that pre-warping constant K. Let's do it without pre-warp. So if we go through, plug this in, now we would get something that looks like that, and we do a little bit of algebra. And I've done the algebra in kind of a clever way here to see the result, how it compares to this. So notice that I've got a k over k plus 1. I've got this over that thing plus 1. So this thing is playing the role of k. And notice that that's just the untangented, is that a word? The untangented omega ct over 2. So that's kind of cool. And that's a good way to think about what's really happening. So the similarity between these, we can just say, oh, let k tilde, we can call this k tilde without the tangent, and now we can write it this way. So we either do the k with the tangent or without the tangent, and we get the same kind of form. And then here is some explorations of this. I used my own little function here that I called LPF underscore bilinear, so you won't be able to find that. But basically, I just did the math that we just saw, and then I evaluated it using freq-z. And I did it for two different cases. So the first case is with an FC that's pretty low. And this was for, I don't really say it, but this was for an FS is equal to our classic 44,100 hertz. And so here's our desired prototype. You can see that will just keep going down at a minus 6 dB per octave or minus 20 dB per decade slope like we would expect from our Bode plot view. And then here are the two designs, both with and without pre-warp. The blue is with pre-warp, and the magenta dashed is without pre-warp. And you see those are virtually identical. Why is that? Well, in this case, the cutoff frequency is way down here, very low compared to FS over 2. So pre-warping is negligible when the feature we're trying to map is very low in frequency. So probably don't even have to worry about it. But let's look at the case where the cutoff frequency is 10 kilohertz, pretty close to that 22,050 hertz, half of FS. There we see a difference between the blue and the magenta, and we see that at 10 kilohertz, the blue is achieving the right response, 3 dB down at the cutoff frequency. The magenta one is more than 3 dB down. Now, that's a small amount, but if you're designing a discrete time system to replace an analog filter, you're going to have people who say it doesn't quite sound right. So you want to make sure that your designs are good, so that you can say, look, there's the plot. It's virtually the same up to, well, beyond the cutoff frequency, they deviate a little bit. But look, this is almost perfect for quite a long time. So here's the trick. If we really do want to implement something with a cutoff frequency so close to FS over 2, a good trick would be to first upsample by a factor of 2, interpolate by a factor of 2, or maybe 3, or maybe 4. Implement the filter. Now we'll have a long range, well beyond the end of audio spectrum, that is virtually identical to the analog filter, and then decimate back down. So there are tricks to do this even better than what this shows. And in that case, pre-warping might not be needed. So really, maybe this pre-warping thing is much to do about nothing. Well, I always do it, just in case. Now, there is a built-in command for MATLAB, and you might think, hey, I've got this nice MATLAB command. Why do I even need to work through any of this stuff? I can just use MATLAB to do it. Here's the transfer function. I take the B's and the A's and I put them into vectors, and then I put those vectors into the bilinear command within MATLAB, and I tell it what the FS is. Or if I want to use pre-warping, I tell it what the FS is, and then I tell it what frequency in hertz I would like the pre-warp to match. And then it will give me the discrete time filter's numerical coefficients. Looks beautiful. Why should I worry about that, K thing and the tangent thing and all that? It looks like I'm all set. Just blindly run a command. Well, in audio, we don't necessarily want just a single fixed design. If you do, knock yourself out. Run the command. But generally, we want to be able to have the user adjust a knob that will change that cutoff frequency. So in many applications, that's the kind of thing that we want to happen. Yeah, there are others where I'm just designing a nice fixed filter and it's not going to be changed by the user. But if you're going to design some audio equipment, users like to be able to tweak knobs and change the sound of their equipment. Then you're going to want to be able to apply the bilinear transform explicitly, not implicitly by just running a command. So let's take a look at how we would do that to map some classic analog filters. So here's just carrying over what we've already seen. And here you see we are doing the pre-warping. So like I said, always a good idea to just do it. It's not terribly hard to do. So here's our two beloved first order filters. These are the classic continuous time filters. And now apply the bilinear transform to these. So that just means plug this thing in where there are S's and do a little bit of algebra and identify the coefficients. And so Zolzer has done that in his DAFX book. He's the editor of that, but the chapter that this is in was written by Zolzer. And so very simple parameterization of the coefficients. So you can have a knob there that the user is going to be putting in the omega sub c values for. You then calculate the K, and then you populate your coefficients, and now you have a filter that will have a cutoff frequency that perfectly matches what the user set with that knob. So that's what I'm saying here. Allows us to set in code any desired cutoff frequency, and we can figure out what the A0, well, the A0 is always set to be equal to 1, what the A1 and the B0 and B1 are. So here's the form that we would end up in. And I, again, want to point out, I think I pointed this out before, that the DASP book, not the DAFX book, but the DASP book has A's up here and B's down here. In DAFX, he's got it right, but in DASP, he's got it backwards from what most people do. So just wanted to point that out. If you go look at the DASP book, keep that in mind. Okay, second order case. Here's our 4 second order, low pass, high pass, band pass, and band stop. And we're just going to plug in for all the S's and do a bunch of arithmetic. Not arithmetic, algebra. But Zolzer has done all that for us and given us this nice table. And so now, unlike for the continuous time case, where we see Q just plays a kind of localized role, we see Q all over the place. So that's kind of an annoyance, and we'll address that at some point to see easier ways to parameterize these things. But still, this is pretty nice. User sets a Q, user sets an omega sub C. So for low pass and high pass, that's cutoff, and for band pass and band reject or band stop, same thing. That has to do with the center frequency. So the user sets knobs that then those numbers get digitized and compute the Q and the K, and we plug those in accordingly. And again, just showing how those go in and pointing out the swap that happens in the DASP book. So next up is shelving filters. We talked about how those are important characteristics or components or building blocks for audio systems. We looked at second order shelving filters. We could do this for first order, but I'm just going to show you how to do it for the shelving filters. In fact, we're not even really going to show too much, just show the results. This is coming out of the DAFX book. And it just shows how to map these things. Just a word of warning, this G here is not the G sub 0 that we had in the previous note set. It's just the V0 value in dB. So it's the amount of boost that you want in dB. It should be a positive number regardless of whether you want boost or cut, right? So if you want to cut, if you want it to dip down to minus 10 dB, you'd put in G equal to 10 dB, you'd calculate your V0 accordingly, and then you'd use the cut form, either low frequency or high frequency cut. So that's the idea. And again, same caveat there. And then peak filters, second order peak filters. We go through the same thing, and again, you can see the two different forms for boost and cut. So these are nice things. You can just code them right in. User tells you what the G value is. You convert the G value to V0. They tell you what the cutoff peak filter. So that's the center frequency. You figure out what the K is. You compute your coefficients, plug them in, and you've got your filter. Very, very nice. Now, as we said, these things are kind of messy, right? We see that the FC and the bandwidth, so bandwidth is related to Q, remember, they've got their fingerprints over all of the coefficients. Now, that's not super problematic, but if you're trying to just shove a simple audio filter into some other system that's running on some embedded processor and you're not being allocated much processing power, these things can be a little troubling because you have to kind of recompute all your coefficients for every time omega sub C and Q are changed. So there's a lot of coupling that goes on in here. And one of the things that is talked about in the audio literature is that we kind of would like to have filter structures that uncouple the effect of these things. Again, not super critical in some applications, but in other applications, very, very nice to have. So some of the things we'll look at in the next set of notes will be aimed at kind of finding these less coupled control through FC and the bandwidth. And one way to do that is all pass filters. All right, I just lied. It's not in the next set of notes. It's in the note set after that, because the next set of notes will talk about all pass filters and see how to use them. But then the note set after that will focus on this uncoupling. So hope to see you there.